Our cosmic address is the observable universe. It's an incredible expanse of space encompassing everything we can currently see. This includes all the stars, galaxies, and cosmic objects within our reach. The observable universe is a sphere, with us standing at its center. From our vantage point, we look out into the cosmos and see billions of galaxies scattered across the vastness of space. When we look at distant objects, we see them as they were billions of years ago. This is because light takes time to travel across the vast distances of space. The observable universe is constantly expanding. However, there is a limit to what we can see, called the cosmic horizon. By observing distant galaxies and studying their properties, we gain insights into the evolution of the universe over billions of years. The observable universe is mind-bogglingly vast. Its radius is about 46.5 billion light-years. To put it into perspective, 1 light-year is the distance that light travels in 1 year. Light travels incredibly fast. It can circle the Earth over 7 times in just 1 second. The diameter of the observable universe is twice its radius, a whopping 93 billion light-years across. Our Milky Way galaxy is only about 100,000 light-years across, making it a tiny speck in the vastness of the observable universe. These distances are constantly increasing as the universe expands. Imagine a loaf of raisin bread baking in the oven. As the bread rises, the raisins move farther apart. In the same way, galaxies in the universe are moving apart as space itself expands. Measuring distances in the universe is a complex task, but it helps us understand its evolution over time. Imagine standing on the edge of the ocean. You can see a certain distance out to sea, but beyond that, the Earth's curvature hides the rest from view. The cosmic horizon is similar. It is the boundary beyond which we cannot see. This is because the universe has a finite age. Light from objects beyond the cosmic horizon has not had enough time to reach us. The cosmic horizon is not a fixed boundary, it is constantly expanding outward as time passes. However, there will always be a limit to how far we can see. The cosmic horizon is a fundamental concept in cosmology. It helps us understand the limits of our observations and reminds us that there is much more to the universe than we can currently see. Section 4. Beyond the Veil, the Unobservable Universe. The observable universe is just a tiny fraction of the entire universe. The unobservable universe lies beyond the cosmic horizon. We cannot see it directly, but we can infer its existence through various observations and theoretical models. One piece of evidence for the unobservable universe comes from the cosmic microwave background radiation, a faint afterglow of the Big Bang. The uniformity of this radiation suggests that the universe was once much smaller and more uniform than it is today. This implies that there is more universe out there than we can currently see. Another clue comes from the large-scale structure of the observable universe, where galaxies are clustered together in filaments and walls, with vast voids in between. These structures are thought to have originated from tiny fluctuations in the early universe, stretched out over vast distances by inflation. By combining observations with theoretical models, cosmologists are piecing together a more complete picture of the universe as a whole. Section 5. Echoes of the Big Bang, the Cosmic Microwave Background. The cosmic microwave background, or CMB, is a faint glow of radiation that fills the entire universe. It is a relic of the Big Bang, providing us with a snapshot of the universe as it was just 380,000 years after the Big Bang. Think of the CMB as a baby picture of the universe, showing us the universe in its infancy. It reveals the seeds of the structures that we see today. The CMB is incredibly uniform, with almost the same temperature in all directions. However, there are tiny fluctuations in temperature, just a few parts in 100,000. These tiny fluctuations represent the seeds of galaxies and galaxy clusters that we see today. By studying the CMB, cosmologists can learn about the early universe, its composition, temperature, and rate of expansion. The CMB is a treasure trove of information about our cosmic origins. Section 6. Gazing into the cosmic past, redshift and the expanding universe. When we look at distant galaxies, we are looking back in time because the light from those galaxies has taken billions of years to reach us. As the universe expands, the space between galaxies stretches, affecting the light that travels through it. As light waves travel through expanding space, they get stretched out, causing the wavelength of the light to increase, known as redshift. It's similar to the Doppler effect, where an ambulance siren sounds lower-pitched as it moves away from you. By measuring the redshift of a galaxy's light, astronomers can determine how far away it is. The farther away a galaxy is, the greater its redshift. Redshift is also evidence for the expansion of the universe, like a giant balloon being inflated. By studying the redshift of distant galaxies, cosmologists can map out the history of the universe's expansion. This helps us understand how the universe evolved from its early state to the cosmos we observe today.
Like and subscribe to start your journey today.